Gabriel, feel free to unmute so you can tell us how it's going. It seems he's not hearing us or is doing something different. Does anybody have any questions about the assignment? Now that hopefully everyone has done it. Okay, Gabriel, do you have liftoff? Thumbs up, thumbs down. Thumbs up? Okay.
Frida's over here too.
All right. So just keep in mind, only one a machine in that room can actually be sending out audio or playing audio. Otherwise, we get feedback loops.
Yeah, I couldn't figure out the audio, so I'm just projecting it from the laptop.
But you can hear me clearly.
Yeah.
Okay, here we go. Anybody have any questions about assignments? The rules of the game are you can unmute and say anything you want at any time. All right. I wanted to mention something that I forgot to mention last time, and that was the idea of certainty equivalence. And that idea is we have to design two things. One is the control law or controller, and the other is a state estimator. And in the assignment, you design them separately. You designed a controller and you designed a state estimator. And an interesting question is, when is it reasonable to design them separately, and when might that cause problems? And it turns out that for linear systems, when you're doing LQR control and something like a Kalman filter, it's perfectly okay to design the controller and the state estimator separately. And the reason for that is that Kalman filter doesn't pay any attention to the control signals. If you look at how it works, except for predicting the next value using the model, the control signal doesn't actually affect anything else. For example, it doesn't affect the
No, but
variant.
you are though. No, you're
Yeah, okay, I'm listening. Or maybe I'm not listening. Okay, that was a message for someone else. Okay. Uh, in general, however, it's not the right thing to design a controller and a state estimator separately. And especially when the systems are nonlinear. Here's a simple example. If I want to accurately estimate the state of something, one of the things I can do is push it into a corner, and then I know exactly where it is. Another example is if I want to know the altitude of something perfectly, I'll just drop it and let it sit on the floor. And now I know where it is. I think I've shown you this before, but I will take advantage of the fact we have a multimedia setup here and show you it again. And here we go. All right, well. That to work. And we want to look at all the videos. Boom. And here we go. So if you watch this robot player after the commercial for Storyteller somethings, you'll see that one of the things going on is that the robot player, and it turns out human players as well, are deliberately driving the ball into corners. So then the system knows exactly where the ball is. It essentially resets the ball. So this shows that, at least in this situation, combining state estimation and control is a good idea. Any questions on that? Okay. The next thing I wanted to do is, I've been trying to show these examples of optimization and how they can solve problems for you. And unfortunately, that was difficult to do on my little tiny laptop and get it set up correctly. The advantage of doing this over Zoom is I could set up things in advance and they're ready to go. So I'm going to run something that computes the inverse kinematics of a two-joint arm. This is essentially what we did before. And what I'm going to do is, instead of using a formula to compute how to reach the point it's currently reaching now, I'm going to use optimization. And on the right-hand side, what's being printed out are the two joint angles and essentially how far away the tip is from the target. And unfortunately, this goes by way too fast. So I put a delay into my code. It's not in the code that I put on the web. And we're going to slow it down. So it gets the shoulder angle right, and then it's approving the elbow angle. And so that's one kind of search. That, if you're interested, that uses a technique called Nelder-Mead, which is often called the amoeba method, where you essentially search a couple points and then figure out which is the worst point and then flip it over a line connecting the other points. And that sort of marches, if you're reducing cost, marches down a hill. And it's a very robust way to optimize simple functions. It does not need to have derivatives of the function available. If you do have derivatives, you can ask the question, at this point, which way is downhill? And that is useful information. So here is a approach that uses derivatives. And you can see, even with that delay, it's much faster. So I'm going to have to delay it more. And you can see initially it takes very big jumps. And my computer just got very excited. Fans went on and everything, but eventually it got to the right answer. Okay, so that's pretty straightforward. So let's look at some more complicated examples. So the example we're going to do now is the situation where we actually have a planar environment, but we have two elbows or three joints. So, and let me get this picture here so you can see the arm. So there, it's trying to touch the red dot. And that, in order to touch the red dot, there are actually many possible answers. So the shoulder is fixed at the center of this figure. And then there's the first elbow and the second elbow. And I think you can see that if you move both of the elbows together, that blue link can move around even with the end of the green link still on the pink dot and the end of the shoulder in the same place. So here, this is actually analytically a very difficult problem to solve because there are many possible answers. You can't just straightforwardly apply the law of cosines, law of sines, but optimization is quite happy to get you an answer. And again, this used the amoeba algorithm to get an answer. Here is, let's just fool around with a couple starting points for this. So, okay, search. So it first got the shoulder pointing toward the pink dot, and then it sort of unfolded the arm. And so you can see, starting from different places, we actually end up with different configurations of the arm that satisfy the goal of put the tip on the blue target, the pink target. Okay, any questions on that? Just feel free to unmute, fire away. Okay, let's just take a look at the approach that uses derivatives. It's actually a lot faster, so I'm going to slow it down. Let's see what this does. Big jumps in the middle, and it gets to the target relatively quickly. And we can start it somewhere else. Okay. Now, how would you set this optimization problem up so that you could choose where the blue link ended up, or make a unique solution to this optimization problem? Any thoughts? Okay, so to encourage people to participate in this situation, it's useful to call on people, so I'm going to do that. Ethan, feel free to unmute. How would you add additional information that would make the optimizer that currently is minimizing the distance from the end of the robot to the pink dot, that would also specify where the blue link goes?
You could include information on the angles from the other joints.
And how would you use that information?
So if you have the angle for the blue link, then you can specify what orientation that's at, and you can use that to minimize the distance of the endpoint.
Okay, let me rephrase that a little bit. You want the endpoint to hit the pink thing, so you're going to penalize that distance. And the way we typically penalize that distance is we square it. And you said, well, we could say we want this blue thing to be horizontal with respect to, the x-axis or something. And we can use forward kinematics to figure out the angle of the blue thing. That would be the angle of the shoulder plus the angle of the first elbow. So, and typically we want to make things so they're always positive, and the usual thing to do is square it. So if we squared theta shoulder angle and first elbow angle, the sum, and penalize that as well, then we're probably going to get a unique answer out of this thing. And so that's a great answer. I did not actually do the same thing. Instead, I said, well, let's go for a situation where the elbow angles bend as little as possible. And I'll show you what that results in. So here we go. Okay. Picture back. Okay, I still have the delay on for this, so it's going to move pretty slowly. So adding the extra penalty definitely slows down the arm. So now it's trying to get closer to the pink thing by bending the elbows, but because of the penalty elbows, it doesn't bend them all that much. And I think this is basically where it's going to end up. Okay, let's put this over here and take a look at what's going on. So what these things are optimizing, I decided to call it a criterion. You could call it a score. This is the delay for the graphics, just does a bunch of square roots. I draw the arm every time we're trying to get a score. I compute where the tip of the arm is using forward kinematics. So let's take a look at that. And the forward kinematics is basically, I figure out the angle with respect to horizontal at each of the links. That's just the sum of the joints so far. And then I do the recursive or incremental kinematics. So the first elbow is at L1 cosine theta 1 and L1 sine theta 1. And the second elbow, well, you start at the first elbow and you extend the next link. And the tip is from the second elbow, you extend the third link. So the forward kinematics is very straightforward, unlike the inverse kinematics. Now that I know where the tip is, I can measure the distance between the tip. This would be the distance squared, and that gives me a score. And then this is a way in MATLAB to print out the three joint angles, which are in a vector called P, and the score. So that's what's going on when I just said move the tip to the pink dot, and I don't care about anything else. Now, what Ethan suggested is, let's change the score function. And the way I did that, I'm still squaring the distance from the tip to the pink thing, but then I have some weight times basically the sum. This ends up being the sum of the squares of all the joint angles with respect to some desired joint angle. And the desired joint angle, I believe, is just 0. So it's the sum of the squares of the joint angles. And you see, I have to choose a weight to trade off doing what I really want and taking into account the other things that I sort of want. And the problem with this approach is I'm going to introduce an error in hitting the target in order to basically try to get the angles to be as small as possible. And if this number is bigger, this weight, this error between the tip and the target is going to be bigger, and the angles are going to be less bent. If this weight is smaller, the angles are going to be bent more, and we'll be closer to the target. So let's test that. So I'm going, right now it's 0.05, and let's make it a tenth as big. And now you have to remember how big that error is. And let me also get rid of the delay. Okay, so that's much closer to the target. But in the and notice when I'm penalizing the angles equally, they end up being basically roughly the same. In this case, exactly the same. And I'm much closer to the target, but the elbows are bent much more. Does that make sense? Okay, Sydney votes yes. Matthew unmuted. Matthew, feel free to say whatever you wanted to say.
I think that makes sense. I was just curious if this always produces a unique solution, because I feel like I could still see a case where, like, at least there'd be one more, because you could have two mirrored solutions to this.
Yes. So in all of this optimization stuff that I'm going to talk about, what the thing finds is a local optima. So it finds a situation where if I change things a little bit, I can't make them any better. So that's called a local optimum. What you're asking for is give me all the local optima, or give me the best local optima. And surprisingly enough, that's called global optimization. And that's a much harder problem. Do you have any ideas how what a simple-minded approach to solving global optimization is? Matthew?
The person that jumps into my mind is more constraints, but I'm not. I mean, you might
How
just
would
need
you,
it
how
like
would you
before
get
what we
it?
did was.
Sorry, say that again.
Oh, before what we did was just do the same local optimization starting from multiple places, see, get multiple local optima, and then you can compare and pick one that's better or that you
Okay.
prefer for some reason.
So the idea is if we start in different places, we might get different answers. And if we start either on a grid or randomly selecting things, we might discover the local optima. So let's actually do that. I'm going to start in a random other place, which is basically the same. So that wasn't very satisfying. It may be that my random starting method isn't random enough. So let's try that. And let's try that. No, I guess that supposed feature doesn't work. So I'm going to just by hand try to screw with this thing. Okay, so it ended up with these. So I'm essentially going to say the starting point is the opposite of all these things. And let's see what we get. Well, I got the thing to flip, and then it freaked out. Okay. How very sad. It seems that I had to give it the transpose, maybe. Let's see what it does. Yes. Oh, oh, okay. It's doing the flip thing. It's not very good though, because with this set of weights, it should get the two elbow angles to be the same. It did not. I'm going to run the gradient thing and see if it does a little better. And the answer is it doesn't. So that's a little strange. Oh, can anyone tell me why this one ended up not being symmetric? I'm open. This actually, I figured it out on the fly. What is going on is we're summing up the squares of all three angles, not just the two elbows. And that means that because the shoulder is in a different place with a value of 1.4, it's trying to become smaller. So it's actually being biased to fold over in the wrong way. And that causes the effect on the first elbow to be different from the effect on the second elbow, and thus it's asymmetric. Okay, so in the chat, someone answered the question that maybe I've asked it, maybe I haven't, which is, how do we get both the ability to apply these extra criteria, which, I want the sum of the squared angles to be small, or I want to be able to choose the angle of one of the lengths, and still hit the target exactly. And in optimization, there's a way to do that called constrained optimization. And what you've seen so far are what are called soft constraints, which generally have the form of where we have some finite weight times a penalty, and we could add more weights and penalties. And we're always going to be trading off errors in what we want with these other penalties. Or you could say to the optimizer, look, I want to minimize this, and I want to exactly achieve the goal, and I want to minimize these other penalties. And that makes exactly achieving the goal what's called a hard constraint. And it's just makes you use a different kind of algorithm. And so I just want to demonstrate that. I'm going to kill this MATLAB so we start fresh. All right. Let's get us a MATLAB going. All right. Here's okay. Now my MATLAB is very unhappy with me for some reason. There we go. Okay. So it is able to hit the target and go to the unique configuration. Let's see if we can start from some other places and get something different to happen. Yeah, okay. sort of weird behavior of the optimizer, but eventually it agrees with the other optimizations in terms of the form of the solution. Let's do that again. So much fun. Okay, so this one, somehow the third link is missing. I don't understand what just happened. So let's try that again. There we go. Okay, so here it failed to find a solution, probably because the blue link was aligned with the red link, and the derivative, this constrained optimizer uses derivatives. In that case, the configuration is singular, the derivatives are 0, so it doesn't know how to break out of that configuration. Let's give it another try. Now there they all locked up. I see now what's happening there. So now they're all aligned. There we go. We get back to the other local minima we started with. Okay, that was the demonstration I wanted to do a while ago. Finally, I got my act together and it works. And the point I want to make is very simple. If we can turn a design problem, such as choosing how to arrange our arm to hit a target, into an optimization problem, we can use the simple part of a coordinate transformation to search for an answer, and we, the humans, don't have to do a whole lot of work. And that's a good thing. Now, you could take the attitude that I don't want to pay any attention in this course. I don't really want to know any of the methods. Can I turn this entire course into an optimization problem? And the answer is, yeah, approximately yes. So a linear quadratic regulator, for example, is a control design that's a solution to an optimization problem. A Kalman filter is a solution to another optimization problem. Now, you might say, well, okay, those work for linear systems, and how do I handle nonlinear systems or complicated systems? And there's a way to organize optimization so that you essentially score every try that a control law is used to get a robot to do. For example, it's called a trial, and you can minimize the cost of a trial. So early on, I said, here are some examples of controlling a rock. So let's take a look at those. And that was the example mass KB manual. And let's see what we got here. Okay, so let me run it and then let's take a look at what it says. So this particular thing, we say init. We should have gotten some graphics. We didn't. Let's see what else we get. Okay, there's the graphics. So what we're trying to do, we have a rock that probably weighs, the mass is 1. And here are some stiffness values. Stiffness is 10, the damping is roughly 6. And that gives you this very nice trajectory that goes to 0. It's done in about 2,000 steps. Our step size is duration over n. Duration is 10 seconds. So this is a kilohertz. It's sampling every millisecond, and it took 2 seconds to get to the goal. And what's being computed here is we set up some arrays to store stuff in. We set up some initial positions, and then we basically go through every time tick. We compute a force, which is stiffness times the distance between the actual thing and the goal, and damping times the velocity. We've computed an acceleration, dividing the force by the mass. We compute a velocity by adding the acceleration times a time step to the current velocity, and we compute a position by adding to the current position the average of the past and current velocities times the time step, and then we plot the position here. Okay, and just for laughs, let's say we want to go faster. So I'm just going to say, let's make the stiffness 20. And let's run the simulation again. Now, it is faster, but we're overshooting. And if I made the stiffness 30 and the damping remains the same, I overshoot even more. And just if I reduce the damping, I jiggle. So I can manually search for the right value of damping to get rid of all those jiggles. I'm going to guess 10. And that looks pretty good. I'm a very good guesser. Okay. Hopefully on the assignment, you tried to do a similar thing with the nonlinear, more complicated balancing robot. And I hope you found it difficult to do by hand. So let's do it using optimization. So let me kill that. Okay, so when we do it with optimization, we declare a bunch of globals, we set values to parameters, we have a duration, we tell the optimizer, we give it instructions on exactly the details of how to optimize. And this is how you call an optimizer in MATLAB. You have a criterion function, an initial set, initial point in the parameter space to start at, and then a bunch of options, which we already defined. And the answer is the optimal parameters. Fval is the optimal score. Exit flag tells you if bad things happened. And let's run it. Okay, where did my figure? Oh, there's my figure. Okay, so what the hell is that? Well, the criterion, what we do is we score 5 trajectories. And I've plotted the 5 trajectories. And they are something that starts at 1 but has no velocity, something that starts at 0 and has a positive velocity, something that starts at 0 has no velocity, that's the green one, something that starts at 0 has a negative velocity, and something that starts at -1 and has a no velocity. And we get the score for each of these trajectories. So we start out with a 0 score and we evaluate something starting at 0, something starting at 1 with no velocity, something starting at -1 with no velocity, and something starting at 0 with a velocity of 2, and something starting at 0 with a velocity of -2. And I plot all of those. And so let's look at what eval traj. Okay, I screwed that up. Okay, so how do we evaluate a traj? Well, we capture the simulated trajectory in a bunch of arrays. We start at an initial place. We do this simulation the same way we did before. We plot them all, and we compute a score by adding up a position penalty, which you can think of as the first element of the diagonal of the Q matrix, and a velocity penalty, which is the second element of the diagonal of the Q matrix. And notice I'm squaring the position error, I'm squaring the velocity. And then for the actions, I have some action penalty times the square of the command. And that corresponds to the element on the diagonal of the R matrix. And we're quadratic in the command. So the idea is we run a simulation for a certain length of time, we score it, and the way we optimize the control law is we guess a control law, we run it, we score it. We try something different, we run it, we score it. If the score decreases, that's a better control law. If it increases, that's a worse control law. Okay. Now what I want to do is, having hidden the, okay, so let's put that over here. I'm going to add a delay to this thing so we can see what's going on. And I'm going to say mains. Well, what are my options here? I'm just going to say main. And as you can see, it tries out different things. It's printing out the stiffness it likes. It's printing out the damping it likes. Let's start it out with some different values, like stiffness equals 1, damping equals 0.1, and let's add more delay. And let's get our pretty picture back. And here we go. Okay, so that very, very quick, okay, that didn't pay any attention to what I told it. All right, so we're going to have to figure out how to screw with this thing. All right. Here's what we want to do. We want to say P0 equals 10. No, we're going to say 20, 0.1. And now it's going to get very excited. And now we run it again. So initially it's unstable, but it figures out eventually I got to increase the damping. So it did that. It's still kind of stuck. I started at a gain of position gain of 20. It's sitting there at 19.9. It's getting the damping up to 2.2. So it's very slowly improving things. You see it plotting the 5 trajectories. Okay, we're getting there. Damping's up to 4.8. So we almost got the damping where we want it. So now we have a situation, the damping's up to 7.5, 8.9, but the stiffness is 19. And the overall stiffness is still, the position stiffness is much higher than the optimum. So the damping's gotten up to 10.5 roughly. So if this thing is working right, it will gradually decrease the position gain. Now, this is ungratifyingly slow, so I'm killing it. I'm setting the delay. I'm getting rid of that delay. So now it's going to fly past. Okay. It cranked it right down to the right answer for this particular setup. A position gain of roughly 1 and a damping ratio of 0.707. Okay, so that worked. Any questions on that? All you have to do is unmute, ask away. So suppose you want to design a control law for a graphical character that you actually simulate the physics of. Well, you could use this method. You could say, I'm going to set the graphics character in an initial state. I'm going to run a simulation for a certain amount of time. I'm going to score it. And then I'm going to, do it again with different parameters and screw around with the parameters until the score gets better. So this particular guy actually did that. Many, many people have done it. These are especially entertaining. So let me get this out here. Okay. And okay. So this is a piece of work called Optimizing Walking Controllers. And his simulation is this blue thing. And the paper describes how they optimize it. And I'm going to play the video. Actually, the video is on YouTube, so I'm going to play it bigger here. Avoiding the advertisements. Okay, so this is after optimization using pretty much the same techniques I've shown you so far. And then they're saying, well, how does human walking work? And the answer is your heel comes down and then you lift it off and your toes bend and you lift off your heel. So we want the simulation to do that. Now, if you manually generate the gains, the right-hand side was what they came up with compared to their optimizer. They started out with an initial controller that, as you saw, fell down. And then they're showing you the optimization after 600, now 1,000 iterations, and it's gradually getting better and better. So one of their things they're penalizing is effort, which is the sum of the square of the torques. That corresponds to the R matrix. They're penalizing here, keeping the head still. They are penalizing how hard you hit the ground. There's an angular momentum term, which is sort of how fast you get things spinning. And on the right-hand side is the hand, the manually designed controller, and the left-hand side was the good one. Now, once you have an optimizer working, you can change the model and re-optimize. So you can optimize something for thin people, short people, stocky people, fat people, tall people. I'll call those thick people. And back to the gorilla. All right. So another thing you can do is during the trials you're optimizing, you can push on the thing. And these red laser beams indicate pushes in various directions. And a question I'm going to ask at the end of the video is, if you live in a world where you get randomly pushed, what's the difference between the controller the optimizer is going to come up with in this situation versus the optimizer the thing comes up where if you live in a world where nobody pushes you around? Here, we're climbing a slope, and the thing they generated for the flat surface didn't work, so they had to re-optimize for slopes. So that means you have to select, I'll call them pre-learned behaviors for different situations. Now they've added a term that says, I'm going to reward going fast or penalize going slow. And this thing starts cranking in a very natural way. Okay, I promised you I would ask the question, if you live in a world where people jerk you around, literally push you around, what happens to your behavior?
You're moving away, resilient to being pushed.
And what would that be, do you think?
Moving especially carefully.
Okay, so you're conservative about, for example, where you put your feet. That's what old people do, by the way. They walk with shorter steps. And the interesting question is, do old people fall down more because they're not as good walkers or because they're paranoid and walking conservatively, which is actually a bad way to walk? Anyway, that's a mystery. It's not yet been solved. Okay, when somebody starts pushing you around, intuitively, what do you do with your arm? Somebody sits there and slaps your arm, and you want to hold it in a position. What do you do? If somebody, you're in a bar and all kinds of people are bumping into you, and you kind of, you're holding a glass, it's full, you don't want to spill it, and you're kind of worried about falling down. What do you do?
Tense up.
Say it again.
Get tense.
And what was the second word?
Tense.
I'm really losing on this. Can you spell it?
Tense.
Tense. Okay, you've mystified me. Anyway, in a subway, you grab a handle. But what else do you do?
Jeez, I didn't think it'd be that intensive.
I can hear you, Gabriel, so you're still there.
I don't know, you pull your arm in.
Okay. What on subways? Do you go subway surfing?
No.
It's so sad, the youth of today. One of the things you do is spread your legs. Get a better base of support. And if you're walking, you could actually spread your footfalls so that they're wider, which will make you more stable to sort of left-right pushes. Now, as you make the adjustments in your gait, what happens if the evil demon that's pushing you stops pushing you? Is your gait still optimal for the situation where you're not being pushed? This is actually
Probably not.
No.
You probably. Oh.
If you already had an optimal gate and you adjust it to handle some new condition, it's not going to be optimal for the old situation. And that has a lot of interesting repercussions. One of the ways when we talk about optimization, we're essentially talking about reinforcement learning as well. And in machine learning, folks are interested in not only generating a reasonable behavior, but generating a robust behavior that works under a variety of conditions. And one of the way they do that is they inject noise into their simulations and try to optimize under those conditions. What that does is it generates paranoid robots that expect to be pushed around all the time. And when they behave in the real world and they're not getting pushed around, they're still paranoid and they behave suboptimally. So that's an interesting philosophical point. So let me show you, this guy also did another paper where he optimized walking controllers for uncertain inputs and environments. And this is an entertaining video. So we'll get through the advertisements here. Free forever. I don't even know what that is. Okay, so that's the optimized walker, and that's the push. So he also looked at, suppose we tell it to turn and stuff like that. So now he wants a robust controller. And as you can see, if you optimize for uncertainty, you can handle that kind of uncertainty. It doesn't necessarily make you good at handling other kinds of uncertainty. And I would argue you're beginning to see changes in the gate because you have this situation where you're being pushed around. So here they're pushing it on a wall and it dies. And here now you see the change gate, so it's less vulnerable to sideways pushing on the narrow wall. And this approach allowed them to develop a simulation they could actually steer, which was nice. So now they're walking on ice and hot coffee. So the baseline controller is pretty jerky. They don't simulate liquids very accurately, but there you go. So this is a different approach to handling being pushed around. And it involves switching controllers so that you can use the optimal controller for the unperturbed situation. But if you suddenly get pushed around, you then start running a controller that's designed for pushes. And I would argue this is very clearly what people do when they're getting tripped. If you trip, you're walking along normally, you get tripped, you have a very fast and powerful response to either plant your foot or lift it up over the obstacle and put it in front of you. And which of those recovery options you choose depends on where you are in what's called the gait cycle. How long has it been since your foot left the ground? So we have two styles here. One is make one controller that works for everything. That's called a robust controller. And the other is make a bunch of controllers that handle different situations and switch between them as needed. And the switching approach works well if you can very quickly and accurately figure out, oh, I have changed conditions before you fall down. The robust controller is useful because then you don't have to diagnose what the situation is. You don't have to identify what bad thing just happened because the robust controller just deals with it. All right. So here we have the humor at the end of their video. And there's the, I think he just stepped over the coffee. Okay. All right, that's enough of that. Okay. Let me show you one other example. So I was involved in a project where we wanted to optimize an exoskeleton, a very simple one, for humans. And the problem is it's hard to get an accurate model of a human. So what we did instead was put the human in the exoskeleton and then run trials with them of a certain length, 2 minutes, and essentially run an optimizer that changed how the exoskeleton worked and optimize it, hoping that the human didn't get tired or anything, that we could optimize for that particular human. So here's a video about that. And
the exoskeleton assistance patterns that
let me
minimize
turn up the volume
for individual humans during walking.
I'll start it over so we get the exciting narration.
During
Soup.
We have developed a method for automatically identifying the exoskeleton assistance patterns that minimize metabolic energy cost for individual humans during walking. During optimization, the user first experiences one control law while respiratory measurements are taken. Steady-state energy cost is estimated by fitting a first-order dynamical model to 2 minutes of transient data. The control law is then changed, and metabolic rate is estimated again. This process is repeated for a prescribed number of control laws, forming one generation. A covariance matrix adaptation evolution strategy is then used to create the next generation. The mean of each generation represents the best estimate of the optimal control parameter values. After about an hour of optimization, energy cost was reduced by an average of 24% compared to no assistance.
Okay. So that's called human in the loop optimization, where you're optimizing the design of something that's supposed to interact with a human, and you optimize it with the actual human. All right. Any questions on that? Comments, thoughts? So the main message there is optimization can be used to greatly simplify stuff. You don't necessarily have to know a lot about what you're working with. You just have to have a way of scoring the performance you care about and some parameters you can change. And the optimizer will figure out how to adjust the parameters to improve your performance. So that's very, very handy in many, many situations. It is the fundamental basis of current work in machine learning. A neural net is something that has some performance, and it has parameters, which are the weights or values in the neural net. And when they say, oh, I'm training a neural net, or the neural net is learning, what they really mean is I'm running an optimizer that's adjusting the weights or parameters of the neural net to improve its performance. So one point of view you can have is pretty much all of AI boils down to optimization. Okay. I wanted to spend the rest of the class introducing you to what's going to happen next. The next assignment is going to be, let's work with a real system. In this case, this robot. And what I'm going to have you do is put it upside down on your table and spin one of the wheels. And here are the experiences I would like you to have. The first thing I want you to do is make it go unstable and play around with that. I think it's really important to get a feel for what can go wrong. And, you know, if you burn up the robot, fine, I'll give you another one. This is what makes the difference between real robotics and just doing math. So far, we've just been doing math, and we've pretended that the math accurately represents the world. Unfortunately, that's only an approximation, and if there are, you know, it is very easy to run into problems and have systems go unstable because of the nature of the approximation and because of the nature of designing controllers. Okay, the second thing that I'd like you to do is model the dynamics of that motor wheel system. The fancy term for that is system identification. Another fancy term is machine learning. But essentially, you're going to learn a model of the wheel, and then you're going to use that model of the wheel to design a very simple controller and a very simple state estimator. And so this is a first step towards doing what you already did in the assignments on real systems. The next step after this, you're going to do the same kinds of things, make a model, design a controller, make a state estimator, but for the right side up robot, the balancing robot. Okay. Any questions on that? All right. So I'm doing the assignment before I give it out to you. I hope to give it out to you probably tomorrow, and then we'll talk about it in class on Thursday. So let me show you the problems I have run into. So okay, so I will show you how to collect data from the robot. Having collected data, it's useful to do things like make models in MATLAB. So I've loaded some data, and I'm going to show you what that data looks like. Once I find my graphics window, there it is. And so the first thing I collected in the data was essentially a clock signal. It's a signal that increments every time the servo runs. And the point of that is if there are any kind of spikes in this thing, it means the timing of the servo is not working. I'm actually running the servo 200 times a second, every 5 milliseconds. Okay, so that seemingly works. Let me actually get this over here. And the next thing I do is collect data from the real encoder. And we'll get back to why this looks the way it does in a second. What I'm actually doing while driving this thing is, okay, why did that happen? Wrong number, sorry. I drove the motor with a sinusoidal command, which made the motor wiggle like this. Now, because the encoder, all I do is get counts, it doesn't know what direction it's going in. And let me zoom into this. And a little taller. So you can see, yeah, that's the up of the sinusoid. This would be the down of the sinusoid, but because we're only seeing pulses from the encoder, it's always going up. So the first problem that we need to solve, or I need to solve for you, is how do we figure out what direction the thing's going in? Now, let me explain to you how an encoder works and how if we were getting two outputs out of the encoder, this problem would go away. So an encoder is typically a disk with lines on it and some sort of photodiode looking at the lines. And every time the line crosses, it gets dark. And when the line moves out of view of the photodiode, it gets light. So what you're seeing is a square wave. And what you count is how many times you see the pulse. Now, that unfortunately doesn't tell you which way the thing is moving. So the next thing you do is you put in a second photodiode, slightly offset from the first one. And then when a pulse comes in this way, one of the photodiodes is activated first and then the other one. So you see these two pulses, and let's say pulse A comes first. And if it's rotating the other way, pulse B comes first. So the way you figure out a direction is you keep track of which pulse comes first, and the way you keep track of speed is count the pulses. Okay, so they're only giving us the A output, and what are we going to do? Well, I'm going to differentiate by subtracting the adjacent values. So this is what it looks like if you just add up the number of pulses. And this is what it looks like if you only keep track of how many pulses came in the last 5 milliseconds. And the top is 10 and the bottom is 0. So you can see the wheel speeds up, slows down, speeds up, slows down. Now, in reality, every other hump here should be going negative, and then you get a nice sinusoid. So how would you solve this problem? Yeah, I didn't know either. So this is what I came up with. If it's moving fast, it's probably not going to change from positive to negative. So the only times when it can possibly change are, let's say, when the difference between, you didn't get any pulses in the last 5 milliseconds, which means the wheel either is going very slowly or not going at all. Now, in a situation where the wheel is not going very slowly or not moving at all, what's going to determine what direction it goes in next, assuming you're not touching it? Ethan, what would drive the wheel in one direction or another?
Um, not sure.
What makes the wheel turn?
The motor?
The motor. And we know what we're asking the motor to do because here's the motor command. So let's take this guy, move it up here, and let's take this. Okay, first, let me choose a set of these things, 1001 to 1500. Boop. And then let's say figure 2. And let's say 1001, 1500. Boop. Sorry, that was the wrong thing. 1001, 1500. All right. So here, the top is the command, and the bottom is what I'm getting from the encoder. I'm trying to align these things. And so at this point, which is, you and I know the velocity is changing sign here. Well, what's going on? Well, the first thing you can say is the encoder, the wheel velocity kind of pretty much looks like the motor command. It's delayed a little bit. So a reasonable model of this physical system is it's like a screen door. It's heavily, heavily damped. Okay. And we can ask the question here, what is the command? And if I get that just right, I think everybody can agree that at 109, what was this one here? Test I'm good. Okay, this is 110. So I want something in that vicinity. Yeah, okay, at 110 here, the command is minus 42. So if we say the command's negative means the velocity should be negative, we then say, oh, it's now moving in a negative direction, and the next possible switch point is here. And we can say, wow, that's a 209. And we'll test how good my visual alignment is. It's 205. Hello. 211. Put it right there. Okay, 208. Anyway, that's positive. So this should switch from negative to positive. So if we pay attention to the command, we can sort out at these potential velocity reversal points what is actually going on. So in theory, that will allow us to recover the velocity. Now, you guys, when you first got your robots, it was running a program from the manufacturer, and that is actually how the manufacturer decides which way the wheel is turning. Can anyone suggest when that's going to fail? And then we'll end class. Brian, when do you think that'll fail?
Could there be like slippage because the wheel is not contacting the ground properly, or is that
Well,
separate?
we want it not to contact the ground here because we want the motor to have total control of what's going on. So what's a situation where the motor doesn't determine which way the wheel is spinning?
I'm not sure. Like maybe I don't think this is what you're looking for, but maybe they like installed it backwards, so like it's flipped.
Okay. I mean, one of the situations which you're going to be very tempted to do is you want to grab that wheel and push on it to see how your control system works. Under those conditions, the assumption that the sign of the motor command determines the sign of the velocity isn't going to be correct. So, unfortunately, we can run our servos, but we can't really test them by pushing on them because that violates the assumptions necessary to handle this. I only have one line from the encoder. If you're wondering, why do we only have one line from the encoder? The answer is they ran out of pins on the Arduino Nano that they use to control the thing. Oh, well. All right. We're over time. Let me stop here. Thank you all very much. If people have comments, questions, complaints, just email them to me and we'll try to make things better. I look forward to Zooming with you on Thursday.
Bye, Chris.
Bye-bye.